Hi everyone. In this video we're going to talk about the inverse of a trigonometric function. Specifically we're going to talk about how we can talk about the inverse of the sine function and the tangent function. So what we have in front of us is the sine function. So if I zoom out you can see that this is the graph of the function f of x equals sine x. And when I think about the inverse function to sine, there's an immediate problem that comes to mind. So if we recall, we know that a function's invertible if and only if it's 1 to 1. And what that means is it passes the horizontal line test. So we can see that even if I just look at the line y equals 0, right, the x-axis, there's a bunch of points that it will hit. So this is a function that it does not pass the vertical line test, right? So you can see that anywhere between -1 and 1, if I draw that horizontal line, it's going to hit in infinitely many places. So what we're going to have to do is we can't actually consider the whole function. What we want to do is we're actually only going to consider a very small piece of this function. Okay. So what I'm going to do is I'm going to try to find a piece of this graph that if I were to just cut out that piece and only consider it and delete everything else, then I could look at the inverse of that piece. All right, so some things that I want for that piece is that it should contain every possible output. So the outputs for the sine function, we have a maximum output here at +1, and we have a minimum output at -1. So I want to choose a piece of this graph that has every output from -1 up to +1, and I would like it to pass the horizontal line test. So as I go around and I look at this graph, one of the things that I think about is these waves right here. So if I were to pick like this top part of the wave, if I have one piece of it, then I can't have the other piece. So if I were to choose to have this section of the graph, well, then I couldn't have this because it wouldn't pass the horizontal line test. So what I want is a top part like this, right? So one of these pieces of the wave, and then maybe the other piece. So if I had this bottom piece, then I couldn't have this one over here. So if I think about this, I want to sort of stitch together a piece that looks like this and a piece that looks like this. Now there's a lot of different ways that you could do that. I could choose to take the region between -3 pi over 2 all the way up to -pi over 2, right? So I could take this section right here of my graph, and you would see that every output from -1 all the way down here, all the way up to +1, they're all represented in between, and that piece, it would pass the horizontal line test. Now, this isn't the piece that we're going to choose. We're actually going to choose this piece over here. We're going to start at -pi over 2, and we're going to go all the way up to pi over 2. So there's a couple reasons why this piece right here is nice. So one, it's centered around the origin. So it includes the origin, which is a benchmark for us. We like to orient ourselves by knowing where the origin is. And it includes the first quadrant. So it includes all of the values from 0 to pi over 2. And so these are going to be particularly helpful when we start talking about inverse trigonometry and triangles. All right, so what I'm going to do is I'm going to take this piece of the graph. So I said we're going to start at -pi over 2, and then I want my x values to go up and stop at x equals pi over 2. Okay, so you see here I've cut out this piece of the graph, and this is what I want to consider. Okay, so here we go. Here's our piece. it passes the horizontal line test, so anywhere I draw a horizontal line will only hit this in one spot, and every output from +1 all the way down to -1 is represented. All right, so if I'm going to create the inverse function, I know graphically what I do is I draw in this line y equals x, and then what I would like to do is rotate this around the line y equals x. Okay, so here's what I've done. I've created this button over here, and I'm going to take this graph and I'm going to flip it around the dotted line. Okay, so that's what we get here. So let's zoom in and take a closer look. Okay, so here's the dotted line is y equals x, and you should see that the red and the blue lines are mirror images of one another. Right, so here's the red and here's the blue. Right, so let's go ahead and turn this off, and let's turn off our sign, and then we get this nice graph right here. Right, so we get this nice graph, and Desmos knows what this graph is. It's called arcsine. Right, so if I write ARCSIN, we read arcsine, and it's the inverse of the sine function. And so here's our graph arcsine and how we created it. Right, so through our worksheets, we're going to learn all about arcsine. Okay. All right, so we talked about the inverse of the sine function. We see here it's arcsine. And now what I would like to do is go ahead and change this around. And instead of the sine function, let's consider the tangent function. All right, so we'll zoom out. And so here's our graph of tangent. So if we go through the same thought process as before, well, if this graph were to be invertible, it would need to be 1-to-1, or it'd have to pass the horizontal line test. And you can see that it doesn't, even if you just looked at y equals 0, right? So you see there's a bunch of points that would hit if you drew a horizontal line. So I'm going to restrict again. So I'm only going to choose a piece of this graph. But what I really would like is to include every possible output. Okay, so I'm zooming out here so we can see that, well, our outputs really are everything, right? So everything here. So we have every possible output. It goes up to positive infinity and down to negative infinity, right? So one of the things that I do know about the tangent function is that it has a vertical asymptote at the line x equals pi over 2. Okay, so let's go ahead and change this around. Okay, so this dotted line, or let's make it a dashed line. So we can see that there's a vertical asymptote at pi over 2, and there's also a vertical asymptote at x equals negative pi over 2. And so we can go ahead and change this around too. So what that means is as I'm approaching pi over 2, my graph is going to get bigger and bigger. The outputs are going to get bigger and bigger. It's going to get closer to this line, and what will happen is it will go all the way up to positive infinity. And as I get closer to negative pi over 2, it will go all the way down to negative infinity. Right? It'll keep going. So if I were to take the same restriction as I did for the sine function from negative pi over 2 to pi over 2, well, I would have a graph that passes the horizontal line test, and it has every possible output represented. Okay, so let's go ahead and do that. Negative pi over 2 is less than or equal to x, which is less than or equal to pi over 2. Okay. Sorry about that. We had a shortcut error. And So now I have a nice graph here. So I've got this piece. We'll turn off our asymptotes. It looks like this graph is passing the horizontal line test, and every possible output for the tangent function is represented. So what I want to do is take this line, y equals x, and I'm going to flip this graph right here around the line y equals x. We see that we get this blue graph here. So this blue one. Okay. So let's clean this up and let's just take a look at our blue graph. Right, so this is a graph. This is what we call the inverse of the tangent function, or it's something that we're going to call arctan. Right, so arctangent of x. We can see the graph here. So Desmos knows what it is, arctan, which is our function arctan. We can see how we constructed it. So we took the tangent function, we restricted the domain to negative pi over 2 to pi over 2. So that made us pass the horizontal line test, and every possible output is represented in that interval. We rotated the graph around the line y equals x, and then we get our arctangent function here. Okay, so if we recall, so our arcsine function looks like this. Right, so this is arcsine, and this is our arctangent function. So we're going to use both of these to help us find angles and to solve some trigonometric equations. So see you next time.